Okay, in 4.6 we are sketching our graphs. So far we've looked at gathering information about various functions using calculus, so intervals on which it is increasing, decreasing, concavity, and then this section utilizes that information to sketch a graph. So I'm only going to do 2 examples in this lesson video, and then while we're in class we can do more examples. So I'm going to take a look at a polynomial and a rational with you. Okay, so first let's take a look at some language here and understand how do we sketch that graph that is increasing and concave down. What exactly would that look like? So if we just imagine part of a curve, this is something that would be increasing and concave down. And then sketching something that is decreasing and concave down also would kind of be the other half. So sketching a function that is concave down and moves from increasing to decreasing, well, we can take those two together and make a downward-facing parabola as one example. And something that's concave up moves from decreasing to increasing would be the opposite, upward-facing parabola. So steps for curve sketching. First, you want to identify the domain. So we're just thinking Algebra 2 here. What background information do you have? You want to find the zeros, which means setting the function equal to 0 and solving. Those are our x-intercepts on our original function. You want to determine the intervals on which the function is increasing and decreasing, and you're doing this with interval testing with the first derivative. And then you can determine the intervals on which the function is concave up or concave down, which is interval testing with the second derivative. Find horizontal asymptotes, or end behavior. This is the limit as x approaches infinity and negative infinity. And find vertical asymptotes, limit as x approaches any value not in the domain. Once you've done all these steps, then you can sketch. So key points that have to be on the graph. You need to find the local min and maxes as ordered pairs. You need to find points of inflection. You need to find x-intercepts and y-intercepts. This would give you enough of a visual of what the graph's behavior is going to look like. You don't have to have all of the exact points in between these important points, but enough to know what the graph is going to look like. Okay, so here's our first example. We're just looking at a polynomial. So first of all, thinking about the domain, anytime we have a polynomial, right, the domain is all real. No restrictions. If we move on to our zeros and we set this function equal to 0, what I'm going to do is I'm going to multiply by 6. I'm going to do that so I can remove both fractions that are in this polynomial. So if I multiply the whole thing by 6, just while I'm factoring the beginning, I will have a 2x cubed minus a 3x squared minus a 12x plus an 18. Just makes factoring a little bit easier. So 4 terms, factor by grouping. Doesn't always work out this way, but it is in this case. I can pull out an x squared, leaving me with a 2x minus 3. Then I can factor out a minus 6, also leaving me with that 2x minus 3. So x squared minus 6, 2x minus 3 equals 0. So my x-intercepts are going to be plus and minus root 6 and 3 over 2. So those are my 3 x-intercepts. Intervals of increasing and decreasing. So this is first derivative test. So f prime is equal to power rule here, so we get x squared minus x minus 2. Set equal to 0 to find your critical points, and undefined, right? But there's no undefined moments here. So if I factor this, I would have an x minus 2 times an x plus 1. So then I'm going to have a 2 and a negative 1. Right. I do need to find complete order pairs for those, but I'm going to hold off on that right now. And I want to do interval testing. So I'm breaking my domain up, negative infinity until -1, -1 until 2, and 2 until infinity. And I'm thinking factored form, is my derivative positive or negative? So if I pick a value like a -5, I would have a negative times a negative, which would give me a positive and therefore increasing. If I pick a number like 0 between -1 and 2, I'm going to have a negative times a positive, which is a negative, and we are decreasing. And if I pick a value like +5, I would have a positive, positive, therefore positive, and increasing. So I can conclude that if I go from increasing to decreasing and the transitional moment is at -1, then I have a maximum there. And then I go from decreasing to increasing at 2, so I have a minimum. Okay, so I'm going to do a very similar process now, but with the second derivative. So f double prime of x is equal to 2x minus 1. Set that equal to 0, and x is equal to a half. Okay. So breaking up the domain, negative infinity, oops, until a half, and a half until infinity. If I pick a value such as 0, 2 times 0 minus 1 is negative, and therefore we are concave down. And then if I pick a value such as 1, 2 times 1 minus 1 is positive, concave up. So there's that transitional moment, therefore we do have a point of inflection at 1/2. Moving on to horizontal asymptotes / n behavior. And if we evaluate our limit as x approaches infinity of f of x, the most important thing here when we have a polynomial, we're remembering that the first term is positive 1/3 x cubed. So if I evaluate just that leading term, that will tell me that on the right-hand side, I'm continuing to grow to positive infinity. And if I look at limit as x approaches negative infinity of f of x, again, just looking at that leading term, we have an odd power, which means the behavior is different on the left and on the right. Okay. There's no vertical asymptotes because there was no domain restriction. And now at this point, I want to come up with my table of values that includes all of those mins, maxes, points of inflection. So if I fill in my table with -1, a half, 2, and 0, because that'll give me my y-intercept, and I go to my calculator or I do this pencil and paper, that's up to you. I'm just going to fill it in for the sake of time. I will get 4 1/6. I will get approximately 2. Doesn't have to be perfect. I'll get a -1/3 and a 3. So then if I go to my graph and I take all these pieces and I pull them together, right? I typically start by graphing my x-intercepts. So I have the square root of 6, plus and minus. And I have 3/2. Square root of 6 I know is somewhere between 2 and 3. So those 2 points are close enough. 3.5 is, of course, 1.5. Okay. I can also plot those other key points at this moment. So at -1, I'm up here a little bit larger than 4. At a half, I'm approximately at 2. 0, 3 for my y-intercept. So here's all the key points that I have. Other things that I found out. I know that as x approaches infinity, the limit approaches positive infinity. So the right side will be ending up. And then as x approaches negative infinity, the graph goes to negative infinity. So the left side will be going down. I know that from negative infinity up until that maximum value of -1, my graph is increasing. I know that -1, 4 1/6 is a maximum. And then between 1 and my minimum of 2, my graph is decreasing, and then my graph is increasing again. I can confirm with concavity, right, from here to here I am positive or increasing. Here to here I am negative or decreasing, and then positive and increasing. And then my concavity showed that from here until my point of inflection, we are concave down or negative, and then concave up or positive. Okay, so all those pieces come together on a graph. Is it perfect? No, but we have all the key components here. Okay. So now let's just take a look at one more irrational function. Okay, we're going to go through all of the same steps in order to determine all of these important points. Oftentimes with a rational function, we don't come up with as many points to graph. So we have to have a better understanding of the concavity, the increasing, decreasing, where these asymptotes are. And then at the end, sometimes we can just find extra points to confirm. Okay, so our domain restriction, right? Domain, we always want to focus on the denominator. We cannot allow the denominator to equal 0. So there's one point of restriction here where x cannot equal 2. Okay. Our zeros, they occur when the numerator is equal to 0. So the 0 here is when 3x plus 2 equals 0, and x is negative 2/3. Increasing, decreasing, so we need our first derivative, and we need to remember that we're using quotient rule. F prime g minus fg prime over g squared. So the derivative here is going to be 3 times 2x minus 4 minus 3x plus 2 times 2 over 2x minus 4 squared. So simplifying the numerator, you get 6x minus 12 minus, make sure you subtract both terms, 6x minus 4 over 2x minus 4 squared, which the 6x's go away, and we just have a negative 16. So when is the first derivative 0, and when is it undefined? Well, it's only undefined. It's never 0 because the top will never equal 0, but the bottom will equal 0 at 2. So we still want to test, even though it's not in the domain, we still want to test our increasing and decreasing around that point. So negative infinity until 2, 2 until infinity. In this case, with this fraction, the numerator is negative always. Denominator is positive always because it's even. This is something that we're going to have to look out for when we transition from the original to the first to the second derivative. So at the first derivative, it's always going to be negative. So therefore, this function is always decreasing. Okay. And there's no true critical point here. At 2, we have a vertical asymptote because it's not in the domain restriction, or it's not in the domain. So now if we go to our second derivative, still using quotient rule, our numerator is negative 16, our denominator is 2x minus 4, quantity squared. So I suggest, even though you could change this and use power rule and chain rule with it, I suggest keeping it as a quotient rule. It'll keep us in a fractional form, and it'll show us a way to simplify that is extremely important here. So when we derive f, negative 16, we get a 0. Minus negative 16. When we derive g, we have a chain rule. So we have 2 times 2x minus 4 times the inner prime of 2. And then we have a 2x minus 4 squared, or to the 4th power. So what we want to acknowledge here is that this first term up top, it's 0. It's gone because there's a 0 out in front. Then we are left with the numerator and the denominator. Before I go simplifying, I need to acknowledge that there's a factor of 2x minus 4 in both places. So I can cancel it from the top and reduce my 4th power to a 3rd power, which is an odd power. And that's significant here. So now I'm going to clean up the numerator, what's left of it. I have a negative 16, so positive 16 times 2 times 2. So I have 64 over 2x minus 4 cubed. Okay. So now numerator is always positive. Denominator could be positive, could be negative, because it's an odd power. So I still don't have a 0 from the top, but I do have that x equaling 2 on the bottom that makes this undefined. So I'm going to break up my interval, negative infinity to 2, 2 to infinity, and I'm going to test. I can use 0. So if I plug in 0 for the x, I would have a negative 4 cubed, which is a negative number. So I have a positive over a negative, which is negative, and concave down. And if I pick a value such as 3, then in the denominator, 2 times 3 is 6, 6 minus 4, so I'm going to be cubing a positive number. So both top and bottom are positive, and the graph would be concave up. 2 is not a point of inflection because, again, 2 is a vertical asymptote, but it still allowed us to see that the graph is going to change behavior. Okay, horizontal asymptotes. So with horizontal asymptotes here, we're still taking the limit as x approaches infinity and negative infinity of f of x. You can use L'Hopital's rule if you want, or you can use the rules from chapter 2. So acknowledging the fact that my numerator and denominator in this original function have the same degree, then I'm just going to be taking the leading coefficients, which is 3 over 2. And it would be 3 over 2 on the right and on the left-hand side of the graph. So therefore we have one singular horizontal asymptote of 3 over 2. Vertical asymptote, we're going to test 2. That is the domain restriction. We should test the left and the right side of 2 to see if the graph has similar behavior. So if I were to pick a number to the left of 2, like a 1.9, and evaluate the original function, which is 3x plus 2 over 2x minus 4 at 1.9, the numerator is positive, but the denominator, 2 times 1.9 minus a 4, that's going to give me a negative. So that shows that this side will be going to negative infinity. If I do the same thing at like 2.1, something really close to 2, but on the right-hand side of it, I will have a positive over a positive. So it's going to positive infinity. So that was important because now I know that on the left and on the right of that vertical asymptote, I'm going in different directions. So keep in mind, we didn't really come up with too many ordered pairs here. We came up with our x-intercept, and that was it. So everything else is going off of concavity, increasing, decreasing, and where these asymptotes are. So what I suggest is just taking some test point to the left or the right of your asymptote to confirm where you think these branches are. Always with rational functions, you're going to sketch your asymptotes first. So we have a horizontal one at 3/2. We have a vertical one at 2. We know we have an ordered pair at negative 2/3, comma 0. We know that we are always decreasing and that we are concave down on the left side of the vertical asymptote and concave up on the right side of the vertical asymptote. The only other thing, I want to take a number like 3, something to the right of that vertical asymptote, and just see which kind of region of my asymptotes does it fall into? I'm thinking it's the top right. So if I plug 3 in to the original function, I would have 11 over 2, or 5.5, which is larger than the horizontal asymptote, so I know that I'm up here. Okay, so that's going to confirm the behavior that I was predicting, and it also is consistent with the fact that at my vertical asymptote, I'm going down to the left of it, and I'm going up to the right of it. It's consistent with my concavity. The left branch is concave down, the right branch is concave up, but both branches are decreasing. So all the pieces are always going to come together for you at the end. Sometimes you have more information than others in order to plot and clearly see it, and sometimes you still have to investigate a little bit more. Okay, in class we'll take some time to go through some trig examples, some e to the x examples, and so forth.